In the last video, we defined a linear transformation and showed that matrix transformations were a type of linear transformation. And now we're actually going to take that a step further. If we have a linear transformation T going from Rn to Rm, then there's guaranteed to be a matrix A such that T of x is equal to A of x. So not only can we say that matrix transformations are linear transformations, we can also say that every linear transformation can be defined by a matrix. So these are actually the same thing. Let's let E1 through En be the columns of the n by n identity matrix. Then we can define A as the matrix whose columns are given by T of E1, T of E2, etc. So if I look where these columns of the n by n identity matrix map to under my linear transformation, I can form my matrix. Let's look at some examples of this. Let's start with the idea of reflecting over the x-axis. Here I have my graph with my axes, and I want to determine the appropriate matrix A that reflects across the x-axis. We know that this vector here, which is my 1, 0 vector, will not change when we reflect across the x-axis since it's on the x-axis. So my first column is just going to remain 1, 0. This red vector is 0, 1, and whenever I do this on the x-axis and reflect across, it's going to move down here. It'll still be over 0, but instead of going up 1, it will go down 1. So the matrix that defines reflection across the x-axis would be 1, 0, 0, minus 1. This time I want to reflect across the y-axis, and I want to find the appropriate matrix A for reflection across the y-axis. If I'm moving across the y-axis, my x vector is going to flip over. It's going to go over negative 1 and up 0. My y-axis will stay exactly where it is, over 0 and up 1. So here's my matrix for reflection across the y-axis. This time I want to reflect across the line y equal to x, which is this line right here. When we do that, our x-axis is going to flip up and take the place of our y-axis. So it's going to go over 0 and up 1. And our y-axis will flip down to the x-axis, so 1, 0. So this will be my matrix for reflection across the line y equal to x. If I change my line to y equal to negative x, and I'm considering this line here, when I try to do my matrix, my x-axis will actually flip down across the line to be over 0 and down 1. And my y-axis will flip across the line to be over negative 1 and up 0. So this would be my matrix for reflection across the line y equal to minus x. I now want to look at horizontal contractions and expansions. And it's going to be easier here to actually consider the full unit box, this full square. The idea of a horizontal contraction or expansion is I'm going to stretch this box over in the horizontal direction. So I'm going to make it a bit bigger here. So my x direction, I'm still going to go up 0, but I'm going to move over by a factor of k. And my y direction does not change at all. So it would still be 0, 1. And if k is bigger than 1, this would be an expansion. We're actually making this thing bigger, our little box bigger. And if it's between 0 and 1, like 1/2 or 1/3, it would be a contraction. We're actually making it smaller. On the other hand, if I want to consider a vertical contraction or expansion, in this case my x direction is not going to change at all, but I will move up in the y direction by a certain factor, or down, depending on if my factor is bigger or greater than 1 or less than 1. But I still go over 0 and up k. So this would be my vertical contraction or expansion. The next one I want to consider is a horizontal shear. The idea being this box is going to turn into a parallelogram being shifted in my x direction since it's a horizontal shear. In this case, my x-axis actually doesn't change. However, the y vector does. It still goes up 1, but it's going to shift over by some factor of k. So a horizontal shear would be 1, 0, k1. If I want to consider a vertical shear, now the idea is I'm going to be shifting some in the vertical direction for my parallelogram. In this case, my y-axis will not change for a vertical shear, but my x-axis will. It's still going to go over 1, but it's now going to change up a factor of k. So this would be my matrix for a vertical shear. The last one I want to consider is a rotation by some theta degrees. As I consider my x and y axis, here's my x-axis being shifted by theta degrees. Well, since these vectors are 1, 0, and 0, 1, we know their length is 1. So this vector is not going to change length when I rotate it, so it's still a length of 1. So I'm actually going to consider the unit circle. The x direction is given by cosine of my angle. The y direction is given by sine of my angle. The y-axis is slightly trickier as I rotate around theta degrees. So I'm going to do some slight work down here. This time, my x is going to be given by cosine of pi over 2 plus theta, since in order to do this, I need to move pi over 2 to get to my y-axis and then theta degrees. And my y-axis is going to be sine of pi over 2 plus theta. And we can use properties of these trig functions to simplify these to be negative sine theta and cosine theta. So this would be my second column. And from here we can actually determine a lot. So if I want to rotate, for instance, 180 degrees, I could say cosine of 180 is negative 1, sine of 180 is 0, negative sine of 180 is 0, and cosine of 180 is negative 1. And now I would be able to rotate 180 degrees. And I can do this for any angle theta.